So we're looking at page 19 in the Unit P packet. The focus here is on unit vectors. And specifically, vectors, when we're talking about unit vectors, it's a vector with a magnitude of 1. And so what we are looking to do is create a basis for any vector space or vector system where we think of a vector that is going off in the same direction as some given vector that we might be interested in, but having a magnitude of only 1. Right? Because when you think about it, the easiest number in existence to multiply by, aside from 0, would be the number 1. Right? So what we're kind of doing is we're creating a ruler by which we can measure the length of vectors in space, and that ruler would be with a basis of 1. All right. Kind of like, if you're familiar with statistics, kind of like the concept of the standard deviation. It varies from data set to data set, but if you can figure out the standard deviation from a data set, then you can measure data points in terms of that standard deviation. All right, that, if you're not familiar with statistics, that might not be very meaningful to you, but that's the general idea. All right, so the concept boils down to the simple idea of taking a vector and dividing by the magnitude of that vector. So, for example, let's say you have something like vector v is equal to, I'll go with the classic simple case of 3, 4. Poor quality close bracket. Right? So the magnitude of that vector would be 5. All right. So it's 3, 4, 5 right triangle. You could also look at it as the square root of 3 squared plus 4 squared. 9 plus 16, 25. The radical 25 gives you a 5. All right. Now u, the unit vector u, would be 1 over the magnitude of v multiplied by v itself. So in this case, 1 over 5 distributed through on that 3, 4. So we would be looking at 3/5, 4/5. All right. So you could verify this using Pythagorean, the Pythagorean theorem. But if you take the squared values of these numbers, right, 3 squared over 5 squared is going to be 9 over 25, plus 16 squared over 25 is, 4 squared, which is 16 over 25, is going to give you 25 over 25, which is a 1. Square root of 1 is 1. So if we can express a vector in terms of a unit vector, then we can use that as a basis to express other vectors in terms of that unit vector. All right, it's a little more advanced, but it's a way in which we can start the process of creating what's called a change of basis. All right, where we're going from the ij vector system to some other vector system. But I don't want to get ahead of myself. What we're going to learn how to do to begin is express a vector in terms of the component vectors I and j. So you're like, well, what is I? Well, I is, sounds wrong when you say that, right? I is, specifically vector I, the vector 1, 0. All right, j is the vector, it sounds a little bit more natural, vector 0, 1. If you find the magnitude of either of these vectors, you'll see that each one of them has a magnitude of 1. All right, so in our ordinary rectangular coordinate system, every vector, every coordinate can be written in terms of those unit vectors. All right, so for example, let's say I have the coordinate, I'll say the vector 3, 4. I'll do that again. We could write that by saying I'm taking 3 steps in terms of the I vector, followed by 4 steps using the j vector. All right, because what that would amount to, and I'll just write it as a check, you know, like old algebra style. 3 as a scalar, excusez-moi, 1, 0, plus 4 as a scalar to 0, 1, so 3, 0, 0, 4, vector addition, whether you do it geometrically or you know, just wrote arithmetic, you would get 3, 4. All right, so it does play out, but this would be the IJ notation, or the linear combination that we would use to express a vector. All right, so the examples below, those are pretty easy now. Most people just look at it and say, oh, okay, so what are we talking about here? We're just tacking a I onto the -2 and adding a j tacked on to the 4. Okay, that doesn't sound too bad. All right, now these arrows kind of get out of hand, so we tend to accept just an ordinary I and an ordinary j. All right, so we would say 0i plus -9j, but then we can apply the rules of algebra. That's the benefit of writing it in this form. Rules of algebra would apply, and we can just say, well, 0 times I would be 0, so -9j. All right, so we're merging or marrying the two ideas together, what we've learned about vectors plus what we already know about algebra and algebraic principles, and by doing so, that allows us to start thinking about how we can apply calculus to this stuff. All right, vector u is a unit vector that forms an angle of 60 degrees with the positive x-axis. All right, unit vector. All right, I got you. So cosine, it's a unit vector, magnitude of 1. So cosine of 60, comma sine of 60. There are some instances where you could just leave it in terms of cosine and sine. We're not going to do that this time. I'll tell you when those instances arrive or arise. So 1/2, comma radical 3/2. That would be the component form. If we want to use standard unit vectors to describe vector u, that's the ij notation. When we get into the third dimension, it'll be ijk. We would write this as 1/2 I plus radical 3/2 j. All right. So we're also going to learn how to apply vectors. All right. We have to, again, tackle the pre-calc stuff before we can handle the calculus stuff. So, you know, some of this will seem kind of simple, and also in the vein of like, why are we doing it this way? I know how to do this with trig. That's kind of the point. We're using the familiar cases, stuff that we know from years past, in order to really enhance our understanding of the vector principles. All right, a jet is flying at a velocity of 500 miles per hour due north when it encounters a wind blowing out to the west at 50 miles per hour. Draw a diagram and use it to find the jet's resultant velocity. I might have said vector before. Velocity, either way, it's going to be fine. To the nearest tenth. All right, so we have, and I'll draw my diagram. We got that velocity of 500 miles per hour due north. So here's due north. So if I'm calling that n, why not call that vector n? N for north, vector n, to represent the direction the object is flying in. All right. The magnitude of that would be 500. We can worry about the units later. All right. There is a wind blowing out to the west. Wind and west both start with a W. Fun fact of the day. Sometimes it locks in at, and I don't know why, but it locks in at an angle that's not quite right, but so I'm just going to throw that in there. So the magnitude of W would be equal to 50. All right. So we want the resultant velocity. Resultant is another way of saying vector sum. All right. So if we combine these two vectors, the impact imposed by these two vectors together, what would it give us? All right. So I'm going to use my handy dandy parallelogram approach. Guess I really didn't need the W. Get out of there, W. Get out of there, W. You bother me. Oh, I did not put my line draw tool on, and that's what you get. Let me put the line draw tool on. All right, see? Now you see what, you know, it's like Wizard of Oz, the man behind the curtain. Now you can see what I really am. All right, so I'm going to draw a horizontal axis here. Oh, now it goes straight. Oh, look at that. All right, well, regardless. This is the 0 degree angle, poor quality degree symbol, so let me fix that. This angle here we know is 90 degrees. All right, this angle here, oh, I cannot draw that. I'm going to try my best. You know what? I'm going to try the line draw tool. Oh, that's so brutal. No, I got to freehand it. It's not looking good. I'm going to live with that one. That one wasn't as bad. 180 degrees off of the zero vector. Or I'm sorry, the 0 degree measure. All right. So if I want to find the vector sum, what I need is a vector that represents n and a vector that represents w, so that I can actually add them together. Now we learned in a previous page, I believe like the very last page, that if we multiply the magnitude by the vector itself, now we'll use the component form, then we'll have it. Now you might say, well, what's the vector? You never told us the vector. Incomplete. Well, it's due north, 90 degree angle, so cosine of 90 comma sine of 90. Now, common sense may tell you that that's 0 and 1. All right, if you're looking for a unit vector in the positive direction, 1 unit up on the y-axis would have coordinates of 0, 1. So we're talking, if we clean this up as much as we can, 0, comma, magnitude of 500. Now for w, it's going to be 50 multiplied by cosine 180, sine of 180. Bring it in now. All right, so 50 multiplied by negative 1 comma 0, which gives me negative magnitude of 50 comma 0. And I know that there were probably some folks that were screaming at the screen saying when I wrote down the magnitude of W is equal to 50, but wait, it's going to the left. It should be negative. That may be the physics approach to things, because you avoid having to deal with the trig in that regard in a lot of cases, depending on the physics class you're in. I want to be fair about that. But here we're focusing not only on the physics, but also the math. All right, so we pick up the signage, all right, SIGN sign, based off of the direction, all right, and the trigonometric evaluation of a function at a particular angle. All right, so if I want n plus w, I'm going to add the two components. So I'm looking at a brand new vector, negative magnitude of 50, comma, magnitude of 500. And again, in the same theme of people screaming at the screen, there's got to be someone being like, couldn't we just use Pythagorean theorem? Yeah. If you were not providing a vector solution. the whole idea here is, again, to take something that we're familiar with and learn about something that we're a little bit less familiar with. Right? I'd like to think that's the reason why you're watching this video to begin with, because it's like, I could use a little help with this vector stuff. All right, so don't think, well, isn't there an easier way? The reason I'm showing it this way is because this is the skill I want you to learn. All right. Yeah, because we could have got to this step right in the beginning, but that wasn't the point. All right. Now, we can crunch the numbers by hand, but this video has gone on long enough, so let me not crunch it by hand. So about 502.5. Oh, that is not a marker. Approximately 502. Oh, that is not a 2 either. A lot of things that this is not. 502.5 miles per hour, so MIFs, MPH. And that would be the resultant velocity, well, to the nearest tenth, indicating that the jet was getting an assist from the wind. Right? It was, it wasn't getting the full 50 miles an hour, but it was